In this question, we've been told that a particle is moving along a straight line and its position is relative to an origin on that line. At time t seconds, the particle's acceleration, a, is given by a equals 6t minus 12. So acceleration equals 6t minus 12. For different values of t, the acceleration is going to be different. Sometimes positive, sometimes negative. At t equals 0, so at the very beginning of the journey, the velocity of the particle is positive 9 meters per second. And once again, at the beginning of the journey, its position is negative 2 meters. So we have two different facts about what was happening at the beginning of the journey. What was happening where t equaled 0. We've been asked to find an expression for the velocity of the particle at time t. So can we just generate an expression for velocity? And also to verify that it's stationary when t equals 3. So let's just start with the information we have. We have an expression for the acceleration. To go from acceleration to velocity, we're going to need to integrate. Integrating acceleration with respect to t is going to give us velocity. So we're integrating 6t minus 12. Just following the normal integration process, increase the power and divide the coefficient by the new power. That gets us 3t squared minus 12t plus c. We always generate a constant of integration. We need to find it, but we were told some information about the beginning of the journey. When t equals 0, the velocity was 9. So if we substitute 0 for all of these t's, the answer we get should be 9, and that will help us to find out what c is. So 3 times 0 squared minus 12 times 0 plus c, and that should equal 9. I hope you can see straight away that these first two terms are just going to be zeros, so we can deduce quite quickly that c must equal 9. So the velocity function in its entirety, v equals 3t squared minus 12t plus 9. That's the first thing we're asked to do, to express the velocity of the particle at time t. Now we need to verify that it's stationary when t equals 3. We're going to substitute 3. We need to think what expression, what result are we expecting to demonstrate it's stationary? Velocity is a variable that tells you the direction and the speed that the particle is moving. So we want its speed to be 0. We want its velocity to be 0. We're expecting all the terms of this expression to cancel out and leave us with 0. Let's check and see what happens. So 3 multiplied by 3 squared minus 12 multiplied by 3 plus 9. All of this we should be able to do in our heads. 27 minus 36 plus 9, and it does indeed get us an answer of 0. So when t equals 3, the velocity is 0, the particle is stationary. Part 2 of the question asks us to find the position of the particle when t equals 2. Well, position, we're going to need the displacement variable to help us with that. So, to find displacement, we're going to integrate velocity. We're going to write out a whole expression. This is why it was important to find c. And we're going to integrate. That gets us t cubed minus 6t squared plus 9t plus a new constant of integration. I'll call it d. We have the original condition that when this journey started, when t equaled 0, when we first started observing this particle, the displacement was negative 2. So, we once again have our initial conditions. We know that when t equaled 0, when we first started observing this particle, its displacement was negative 2. Its position on the line was negative 2. So, let's use this initial condition to find the value for d. So displacement, we're going to substitute in zeros. This is once again going to generate a number of 0 terms. So all of these zeros plus d equals negative 2. D equals negative 2 helps us to rewrite the displacement equation. S equals t cubed minus 6t squared plus 9t minus 2. The question has asked us to find the position when t equals 2. So substituting 2 into this expression we've just found will give us that position. So here we go. 2 cubed minus 6 times 2 squared plus 9 times 2, and then subtract 2. That's 8 minus 24 plus 18, subtract 2. Altogether gives us 0. The displacement from the origin when this particle has been travelling for 2 seconds is 0. It's sitting on the origin. Be careful, this doesn't mean that that's where it started. It's just where it is after it's travelled 2 seconds. It started 2 meters away from the origin. 2 seconds later, it's exactly on the origin.